Nathaniel?
One of the Nathaniels of HamSCI, I guess.
Yes, there's more than one Nathaniel of HamSCI. What do you think about that?
Yes.
Ooh. Yes. So that is Nathaniel KB1. QHX, yes, QHX. So Nathaniel Vishner, KB1QHX, is on the local organizing committee here at Case Western Reserve University and is a very active member of W8EDU. And is there anything else you'd like to say about yourself?
I guess this is my fault that we're here again. I just want pizza. If you want more of that, stop by during the poster session. I'll give you the short and or longer version. Also, W8EDU has gone into the clock business. You may have seen clocks downstairs or on the order page. They're ultra-atomic clocks from La Crosse with a custom face. We have more to sell if you would like to buy one and didn't pre-order.
They are absolutely beautiful. So I strongly recommend it.
Yes.
All right, Nathaniel, yes. KB1QHX, why don't you take it away and introduce our next speaker?
Okay. Our first speaker of the session is Dr. Chris Deacon, G4IFX from the University of Bath, on why is sporadic-E propagation so weird?
Thank you. Before I start, are there any 6-meter operators in the audience? Oh, what's it? Well, you guys know that sporadic-E is weird, right? It's weird. It appears when it feels like it. It's called sporadic because it's sporadic. It's very, very difficult to forecast, although we know it happens mainly in the summer and late in the morning and late in the afternoon at the sort of the peak times. But it just sort of comes and goes. Signal strengths vary enormously, if I don't break everything here. One of the reasons that I suspected that the signal strength varies enormously, there are clearly multiple reasons for it, is rotation of the polarization of the reflected wave, and that's how I got into my PhD study. So what I'm going to talk about today, I'm going to assume, rightly or wrongly, that people are happy enough with the concept of sporadic-E. I mean, because it's been covered in previous HamSCIs, I've presented on it myself. Jim Bacon gave a tutorial on it a couple of years ago. But it's formed by a different mechanism than the rest of the ionosphere. Key point number one. It happens in the E layer, but it's embedded in the E layer, but that's pretty much the only connection it has with the E layer. It happens at about, I think Phil yesterday said something about the 100-kilometer the Kármán line, where interesting interactions between the lower atmosphere and the upper atmosphere are happening. And that's why actually the academic world is still interested in sporadic-E, despite the fact that television is no longer broadcast in the low VHF range. So I'll briefly summarize the results of, essentially my PhD research in terms of whether the nature of the polarization of the signals reflected from sporadic-E. Fortunately for me, we just had a fantastic introduction to ray tracing and so on, so I don't need to do any of that, which is good because I wasn't going to anyway. So let's sort of crack on. So back in 2018, which was pretty much solar minimum, I conducted a measurement campaign in Europe, monitoring a whole half a dozen beacons. You have to do it on an opportunistic basis on 6 meters at 50 megahertz. You can't rely on a signal being there on a particular day. Forget VOACAP or whatever. You can't do that. Most models of sporadic-E don't. Sorry, most ionospheric models don't model sporadic-E at all, simply because it's very difficult to forecast. So it's made of a different mechanism. It's not ionized gas; it's ionized meteor debris. The ions are much bigger than the ions of oxygen, nitrogen. Therefore, they're much more affected by the winds. especially in this sort of 100 to 130 kilometer height range. But of course, they drag the electrons, just simply from the Lorentz forces, they drag the electrons around. And wind shears at that height concentrate those ions into very thin layers. And a typical thickness of that layer is a sort of 2 kilometers. So I started off doing this simply because I just wanted to know. I wanted to know what happens to the polarization. Is it the cause of what I see? So I started doing research. I actually reconfigured my own 6-meter station at home to have a dual 7-element Yagi about 20 meters above the ground. 6 meters is a good place to try and measure polarization. It's quite hard to measure polarization because it's hard to get your horizontal and vertical samplers, which is effectively what you're doing. You're sampling the incoming wavefront on these antennas. You're hard to get them in an identical circumstance. If you're too close to the ground, you need 2 identical antennas if you possibly can. So what you see there is a pseudo real-time replay of the incoming polarization from a particular beacon. It was in the Faroes. This was an opening that lasted over an hour, which is quite unusual for sporadic-E. But the signal was going up and down all the time. So this is live. I used an SDR to capture the I and the Q, the complex amplitude of the incoming signal, and from that you can derive the properties of the polarization ellipse. And you can actually convert it to circular coordinates, in fact. So when it's red, that's left-hand polarized, circular, left-hand elliptical, and when it's blue, it's right-hand. And as you can see, it's constantly changing on a time scale of seconds. This is like real time here. It's only a minute sample, but it's sort of real time. So it's rotating, it's changing from one handedness to the other pretty much the whole time. So if you then look at across, in this particular case, there's only actually one opening, but 40 minutes worth of data. Oh, by the way, just characterizing down the bottom right here, if I can use this pointer, down here, we have the way that the polarization of an ellipse, or any ellipse, but polarization ellipses are measured. You've got the shape of the ellipse, this thing called axial ratio, and you've got the angle that it sits at. And on the left, there are 2 histograms. Each of these histograms has about, as it happens, because this was a long opening and I was sampling at 6,000 samples a second. By the way, I only did that because that was the slowest my Apache Labs receiver would do. There are about 14 million data points in this histogram. So it's pretty good for that day, but probably on a different day, it probably would look different. So on the left, you have the axial ratio. 1 is the red line in the middle. And that's circular. So you can see it was circular some of the time. The high numbers over to the left-hand side and the right-hand side of this axial ratio. Can you imagine if the long axis is 1,000 times longer than the short axis, you've pretty much got linear polarization. And what that's showing is that it's elliptical the whole time. Now this was transmitted, I've seen a photograph of the antenna. Is transmitted with sort of pseudo-linear polarization, horizontal in this particular case, and you can see it actually spends most of its time around, I don't know, 3-4 axial ratio, and you can see that in the rotating picture on the right. The right-hand chart is the tilt angle, the angle that the ellipse sits versus the vertical, and you can see there's a sort of a preferred angle over here, but in fact it rotates. Well, yeah, as you can see, it's rotating all the way around. So it's not only elliptical; it's constantly changing. And the reason, although my original research was all on the basis of I just want to know the answer. The research question became, what is the mechanism for the reflection from sporadic-E? Now, Kate was talking about how refraction happens in the ionosphere, reflection happens on the ground, although most people historically have thought of sporadic-E as being reflection. And I wanted to find out whether that was realistically true. Thesis being, if it's elliptical, then, and it's changing, then it can't be either linear and it can't be scattering either. And I think this research did demonstrate that. Here's a summary of the 6 beacons that I have recordings of. This is a little known region called Europe. And that's a little, I was actually somewhere where they had a map of Europe on the wall the other day, and they'd missed off the UK. I think they were making a political point. Okay, so the red dots are where the beacons, I mean, there are other beacons marked on here simply for comparison, but the red ones are the ones that I've actually got significant data from, ranging from the Faroes in the north at about 1,250 kilometers down to Spain, across to Hungary, Slovenia, Italy, and Sardinia. Every single one of them is elliptical the whole time. Every single one of those beacons transmits linear polarization. Ergo, the mechanism has to be magneto-ionic. It has to be something that follows obeys the Appleton equation, which is the nasty one that Kate put up when you all went when it came on the screen. Fortunately, you don't actually have to do that yourself, because ray tracers will do that for you. Just to look at 2 of them, though. No, backtrack slightly. So I've demonstrated, I think, that the propagation is that the way the reflection happens is magneto-ionic. It is refraction. Yeah. But to be a bit more convinced about that, I wanted to be able to, well, 2 things really. Firstly, demonstrate that magneto-ionic theory can actually produce the kind of effects that I'm seeing. And secondly, this one's really weird. Yeah, because these 2, Slovenia to the UK, Hungary to the UK, they're both east, close to east from the UK, so they were the signal was traveling west. Slovenia, which I monitored on 4 different days, you've got the dates there, was entirely left-hand polarized, which in the northern hemisphere, if you remember, Kate talked about the O mode and the X mode, the ordinary mode and the extraordinary mode. That's ordinary. That's the ordinary mode. And its tilt angle, the way it's measured, if it's negative, you're in the top left-hand quadrant. Was in the top left-hand quadrant. Whereas Hungary, very similar path, which I actually managed to record on 6 different days, it's right-hand polarized, which is the extraordinary side. Although one thing I do know is that both modes are present all the time, and I'll explain why that is, why I know that in a bit. And the tilt angle was on the top right, not top left, top right. Okay, so I've been trying to answer that question, or get insights into the answer to that question, by doing ray tracing. I've been using FarLab to do that. Conscious of the constraints that Kate was talking about. You're talking about a relatively short wavelength, but by the way, it is affected by the ionosphere. In fact, now, at the moment, there is global F2 layer propagation happening on 6 meters. Unfortunately, it doesn't happen in latitude 51 very much, although hopefully it will do that again. It has done a little bit. The primary mode, propagation mode for DXing on 6 meters across the whole solar cycle, because it's not really affected by the whole solar cycle, is actually sporadic-E, which is why it's interesting. So if you look on the left-hand side, that's actually not a 6 meter signal that I've modeled there. But this is just to illustrate that when your linearly polarized wave goes up to the ionosphere, that Appleton equation, it's not actually sitting there thinking, I'm going to solve the Appleton equation now. But there are only two solutions. There is not a linearly polarized solution. There are the ordinary mode and the extraordinary mode, which are in general elliptical. They have opposite senses of rotation. And this is actually a 1 megahertz signal, just to illustrate the effect. And the thing is that they get refracted at different heights. The extraordinary ray tends to bend more suddenly. And as was said, the ordinary mode tends to go slightly higher. And they land in different places, typically. Now, that happens even at 6 meters, even at 50 megahertz, but the distance between those two landing modes points is much smaller. But I still need to be able to land two signals on the same place, my antenna. I want to land these two in the simulation on the same place because I want to try and measure the phase difference between the two waves. So I've got an algorithm, a bit of code, whatever. There was a phrase for it anyway, Pathfinder or whatever it was. I didn't know it was called that. And so, in fact, to get two rays that land in the same place, this X and O ray, they have to be launched at slightly different elevation and azimuth angles. So the way I've modeled it is that I've taken IRI, the aforementioned International Reference Ionosphere, and added sporadic-E on top of it, so that what you get is the electron density is that top trace there. And you can see that the electron, this is a fairly intense bit of sporadic-E. It's about 2 kilometers thick, which is fairly typical. It's sometimes less, it's sometimes more. But it's a huge, the electron density is 10 times as high as the background E layer. And the critical frequency, the plasma frequency, the minimum frequency, maximum frequency, sorry, reflected straight up and down is also a lot higher. So some findings from building that model. Firstly, it actually does work. That sporadic-E layer is very simplistic. It's a raised cosine. It's of infinite extent across my ionosphere. But if you look at this chart over here on the left, what I've got on there are the sporadic-E path. By the way, the E region is sort of light green, if you can see that, and the sporadic-E layer slightly darker green on this chart. From between Hungary and the UK at 50.430. I also modeled it on the same day from Hungary to the UK on 7 megs, and it happened, we were talking solar minimum here, it was in the afternoon, middle of the afternoon, and it was actually an E-layer reflection that operates at that time of day. The thing to notice is, they both bend. The sporadic-E one doesn't instantly reflect, but it reflects a lot more quickly simply because the layer is more intense, but also it's so thin by comparison. So the sporadic-E bends in terms of, over the path, it's about 7 times as fast as the 7 meg. So it's refraction, but it's very quick refraction. Secondly, if you look at the angle on these two particular paths now, between the ray angle to the magnetic field of the Earth, which, and they're both vectors, by the way, which is why it can be greater than 90 degrees. The Hungary to UK path crosses the 90-degree point. 90 degrees is perpendicular to the Earth's magnetic field. The polarization, without going into it in any detail, the polarization of the characteristic wave changes as according to the local magnetic field and the local electron density, and some effect from the local collision frequency as well. So actually, when it's going right there, when it's on 90 degrees, it has to be linear. That's the only way that the polarization, but it's still the ordinary or the extraordinary ray, but it turns linear and then it comes back out elliptical again down the bottom here. The Slovenia one actually crosses the 90-degree point twice. I don't know if that's, in fact, the first crossing is actually in the E layer, not the sporadic E layer. So I don't know whether that has an effect or not. So a couple of other things that initially came out. Firstly, I need to put a higher FOES, it's known as the sporadic E critical frequency for the ordinary mode straight up, which is directly related to the electron density. I had to put a higher FOES into the model than was represented by any of the ionosondes I was looking at. That's either because sporadic E happens when you get an intensity. There's a lumpiness to sporadic E, and often the reason the signal, in fact, both of my recordings on that particular day, in the middle of August, were about 2 minutes long. It appeared, it was there, and it had gone in both cases. Total absorption, I'll maybe explain why this is important, but absorption is small at 50 megahertz. It's a high frequency. So ionospheric absorption, at least according to the model that's built into FARLAP, is very similar. And I was using a slightly tweaked version of IRI there called the Faraday IRI, just to try and get that as well as possible. But it's significantly less than 1 dB. And by the way, the absorption for the two characteristic modes is the same anyway. Further findings. FARLAP now has the ability to calculate the coupling factor. You've got a vertical one. We know that the ordinary and extraordinary rays are elliptically polarized. There are different angles here. It'll actually calculate the ratio that goes from my vertical antenna into O mode versus the proportion that goes into the X mode. Both paths are about the same. There's a ratio of about 2.5 dB, 2.25, 2.47, whatever. I mean, I'm not suggesting this is totally accurate, right? As was said earlier, the one thing you know about your model is that it's wrong. But I'm just trying to get insights into what's going on here. But very interestingly and usefully, the downward characteristic modes, I said the polarization of this signal changes as it goes through the ionosphere, is very close to circular. They're both the same. Both O and X have the same axial ratio. The ellipticity is the same in both cases, but one's right hand, one's left hand, and they're also at different angles to the magnetic field. This is actually a simulated ellipse. I've got some code that will, I can input 2 circular waves, and it tells me what the sum of those 2 circular waves comes out as. And this is an axial ratio of 1.25, 1.05. I think if I took those boxes away, you'd struggle to tell that from a circle. Couple of interesting points, which is backed up in the literature. If you're adding 2 orthogonally polarized circular waves, the tilt angle, the angle that the total signal, and this happens at the antenna, by the way, effectively, it happens at the antenna, is half, it really is, half the phase difference between those 2 circular waves, if you can assume they're circular. That surprised me at first. It is actually discussed in the textbooks in the context of Faraday rotation, which is a special case of what I'm talking about here. But I've actually simulated it, and yes, it really is independent. It's also independent of the amplitude relationship between those 2 signals. And the net axial ratio and rotation sense depends on that amplitude variation. If they're both the same amplitude, whatever else is happening, you've got a linearly polarized signal. But the angle of that linear polarization varies according to the phase difference. If it's circular, then you've only got one of the O and the X. Since I've been getting consistently elliptical, not circular, not linear, most of the time, that demonstrates that both O and X are present. Okay, so now Phylap does not. One of the things I'd love it to do, although I can calculate it myself, which I'll have to do, is it doesn't actually expose the full sort of polarization details. There's the complex part of the polarization. By the way, there's an equivalent to that. It's called the Appleton-Hartree equation, the one that does the refractive index that was up on the screen earlier. There's an equivalent, an inversion of that for polarization. To fully know the polarization, including its rotation sense and so on, you need to have the full complex value, which it doesn't do, unfortunately. Or at least it does do it. It must do it inside the calculation, but it's not exposing that data. But there is a way that we can get at part of the polarization, and that is all around the path length. It tells you the phase path length. Also tells you the group path length, but that's by the by. This was useful for two reasons. Firstly, this representation is plotting the phase path length for the ordinary mode, wrong thing, up here, and the extraordinary mode down here. You can see there's some variation, there's some noise on that. And this was on a particular, fairly simple 100 kilometers, 2 kilometers thick sporadic-E layer. And it gives me a roughly quarter wave path difference between those two. Now the bumpiness, the lumpiness, tells me something about the stability of the solver, the actual numerical differential equation solver. If I bump up the electron density, or I reduce the thickness too far of my model sporadic-E layer, that goes crazy. Those two sets of lumps just overlap. And essentially, what that means is that a tiny difference in. By the way, this is across the wavefront, roughly sort of 100 meters wide and 30 meters high. So there are two sets of. There's a fan of rays, which I'm modeling here. And what it's showing is you've got a reasonable consistency of the phase path calculation between that. But as I say, if I push it too far, and I am actually at the edge of the capability of the numerical solution, I've got the minimum tolerance, the tightest tolerance that you can have. If I relax the tolerance, by the way, it also blows up on this. So what I've got then is a way of measuring the phase difference, or simulating the phase difference between the ordinary and extraordinary modes, and therefore, according to what I was saying before, calculating the phase difference, the path difference, hence the phase difference, hence half of that is the tilt angle. So here are my two signals on one particular day now. I chose these because it was so neat. You know, they're actually, one is 10 minutes after the other, both on the same day. So it can't have been a dramatic change in circumstances, or indeed my equipment. You can see that the one on Slovenia is consistently top left hand, left hand, and the Hungary to UK is consistently top right hand, and you can see the sort of median shapes there during that. And it turns out these are actually slightly extreme, but versus the average. But nonetheless, it's a useful demonstration. And I was hoping to be able to use Ionosonde data to by the way, this was the subject of my last talk here, virtual, but 2 years ago, about using amateur reports. This is from PSKR, from WhisperNet, and so on. The green blobs, the green dots are 10 meters, 28 megs. The blue dots are 50 megs. At that particular time, there wasn't any 4 meters there. You can see, by the way, that the extent of the green ones is wider. And I can tell you, across the whole afternoon, I've got a video of it, the whole afternoon, the 10 meters were spread out more widely than the 6 meter ones. So you've got a sort of a region of sporadic-E, which has got concentrations in it, which are constantly, A, moving, and B, varying. And there are the ionosondes that are active in Europe. The trouble with ionosondes is they're too far apart. But we know that, and that they're expensive and so on and so forth. So that's where those two paths look. That's what they look like when they're plotted on that map. Now, they are actually about 200 kilometers apart. When you think that a sporadic-E cloud could be 10 kilometers wide, it wouldn't be entirely surprising if there were different conditions in place in those two places. I was hoping that I might get a degree of commonality, but unfortunately, it didn't really work out that way. The Ionosonde data wasn't very helpful. I was hoping to be able to plug in, okay, the critical frequency was this, the height was this, the thickness was that, and simulate it. It didn't work that way. As I said, the FOES that the Ionosonde's recording seems it's lower than what I'm seeing. The height and thickness resolution of an Ionosonde is about 2.5 kilometers. Usually, which is not great for making accurate measurements of height or thickness. Well, at least not at the level that I'm talking about. And the virtual height. Now, this graph, the bottom one is from these are the three ionosondes which are closest to those reflection points. One in Hungary, the bottom one in Czech Republic is the middle one, and Belgium is the top one. And they're all different, aren't they? So it didn't really tell me what I wanted to know. So assuming, which is what I observed, that the sporadic-E cloud was sort of moving east to west over a period of maybe an hour and a half, I sort of started around this sort of height, so 98, something like that. And I managed to simulate, and I think this is at least shows the principle of what's going on here. The tilt angle of both of my ellipses, and it looks like this. So I found that in order to make the Hungary one work without blowing the model up, without increasing the critical frequency even more, without reducing the thickness of the ES layer even more, I had to go lower. With the Slovenia one, I actually had to make the path length difference between the two longer, because a longer path length corresponds, if you like, simplistically to the top left quadrant on that ellipse thing, and the shorter path length, and this was unusually short, the path difference on Hungary. So I've managed to simulate. I'm not suggesting this is exactly what was happening, but it's giving some insight into what was going on here. I've used the same height for both of them, because that probably seems to be the most consistent thing. Virtual height and real height are going to be much closer together, by the way, for sporadic-E than they would be for the F layer or E layer, simply because the layer is so thin in the first place. So where does this get me? So I've applied in more detail now, rather than just saying, well, is it elliptical or not, which is what I was doing before, magnetoionic theory to the incoming polarization. It predicts the tilt angle. I can make it predict the tilt angle of the ellipse that I actually observed. This is that Faroe Islands one in there, just because I wanted a picture on this page. The model is showing that the tilt angle is confirming that the tilt angle that you receive of the ellipse, by the way, is not surprising if you get a lot of QSB, as we call it, a lot of fading on a 6-meter signal. If it's fairly strongly polarized and it's rotating all the flipping time, sometimes it's going to be aligned with your horizontal antenna, sometimes it's not, and you can get some really big dips because of that. I've modeled the phase difference over quite a wide range of ES layer characteristics, and I can actually move that by simply making different assumptions. Here, I've been trying to match reality, but if I make different assumptions about the electron gradient and so on in the sporadic-E layer, I can move the whole thing round in orientation, the ellipse. But there's clearly an amplitude difference between the O and the X. It's not due to the coupling, as far as I can see. It's not due to absorption, as far as I can see. But I haven't got an explanation for that, and I suspect that ray tracing is not going to do that. There is a whole load more data. The common mode fading, and that's something else. That's for a sort of future exercise. So there I am. Those are the papers that I published it all in. My thanks particularly to Catherine Mitchell, Ben Whitfleet, who some of you may know, and Rob Watson, who've been my advisors in American Speak over this. Thank you.